Okay, so today we're diving deep into something pretty fundamental.
Fundamental, yeah.
Like the fundamental building blocks of everything.
Yeah.
Quarks and leptons, and we've talked about these before, of course.
Of course.
But what really got me interested this time around was a series of YouTube videos I came across by a guy named Juppa Buckner.
Yeah, I saw those.
And he's got some really interesting ideas about how these particles might actually get their mass. So what I'm really hoping we can unpack in this deep dive is how well this model that he's presenting, aligns with the standard model of particle physics because, that's our best current understanding of, the universe and the particles in it.
Absolutely, yeah.
But the standard model doesn't really explain why these particles have the masses they do.
Yeah, it's one of those big open questions in particle physics.
So we'll be looking at some specific calculations from the videos. And we're going to be talking about top and bottom quarks charm and strange the up and down quarks, and then all those leptons, the pow, the muon, the electron, and all their corresponding neutrinos.
Yeah, and those neutrinos are always a bit of a mystery.
They really are. Yeah, they're so elusive.
So it'll be interesting to see what this model has to say about them.
Right, exactly. So let's jump right in and maybe start with the heavyweights.
All right, let's do it.
The higher generation quarks. And at the top of that list, literally in terms of mass, is the top quark.
So according to this model, the top quark is made up of a generic component, and that has a baseline mass of 200 electron units.
Okay.
And then it's got a scalar boson plus.
Right, so a scalar boson plus.
And then it's at this point where this concept of combinatorial values comes in.
Okay, combinatorial values. This sounds important.
It is so, imagine them as like charges. You know how particles have electric charge?
Yeah.
Well, in this model, each piece of the particle system, like the generic quark and the scalar boson, they each get a combinatorial value.
Okay.
So for the top quark, that generic Descartes, it has a combinatorial value of 1, and the scalar boson plus has a value of 2.
All right, so 1 and 2.
And here's the rule. If the sum of those combinatorial values isn't equal to 1, then that scalar boson is going to introduce what he calls a mass factor.
So 1 plus 2 is 3. So that's not 1. So it's going to have a mass factor.
Exactly.
Okay, so how big is that mass factor then for the top quark?
So for the top quark, it's 200 times the initial mass of that generic component.
Wow, 200 times.
So we start with that 200 electron units for the Descartes. But then there's this other really interesting twist.
Okay.
So the electromagnetic factor associated with this boson, plus it actually transforms this generic D-type quark into a generic U-type quark.
So it goes from a D to a U?
Right, and that electromagnetic factor that kind of represents how the electromagnetic force can influence the fundamental identity of these components.
Right, like the electromagnetic force is kind of messing with it and turning it into a U.
Yeah, exactly. And in this model, a generic U has a mass of 2,000 electron units.
Oh, wow, so it jumps way up.
Yeah, and then if you take that 2,000 units and you multiply it by that mass factor of 200,
oh boy,
that was triggered by the combinatorial values, you get a final mass for the top quark of 400,000 electron units.
Wow, that's huge. That's how it gets so heavy.
It is, yeah. That's why it's the heavyweight champ of the quarks.
And you said earlier that the signs of these combinatorial values, like whether they're positive or negatives, can also affect the mass.
Absolutely, yeah.
So how does that play into the top quark situation?
So the rule is, if you multiply the combinatorial values together, and you get a positive result, like positive times positive or even negative times negative.
Okay.
Then the mass factor is going to increase the overall mass. And in the case of the top quark, we had a positive 1 and a positive 2. So a positive product, meaning a big mass increase.
Okay, that makes sense. So let's move on to the next heaviest, then the bottom quark.
Right. The bottom quark or the B quark.
So what's going on with that one?
So it's made up of a generic D, again, starting with that 200 electron unit mass.
Okay.
And then it's got a boson 0.
A boson 0, okay.
And just like the top quark, the sum of the combinatorial values of the bottom quark system isn't equal to 1 either.
So we're going to have another one of these mass factors popping up.
You got it.
Okay.
And in this case, the mass factor for this particular boson 0 is 2.
So 2 times that initial 200 would be 400.
Right. But then the model adds another layer here.
Oh boy, more layers.
Yeah, there's actually another boson 0 hanging around in the bottom quark system. And this one has a combinatorial value of 20.
Oh, wow. So that's going to really crank things up.
Exactly. It acts like another multiplier on top of that 400 electron units we already got.
So 400 times 20, that's got to be like 8,000.
You get 8,000 electron units for the bottom quark.
Wow. So these combinatorial values can really have like a domino effect on the final mass.
Yeah, they can really cascade and amplify things.
Okay. All right, let's move on down the line to the charm quark.
Okay, the charm quark.
What's its story?
So the charm quark also involves a generic D starting at that 200 electron unit mass.
Okay.
But in this case, it's paired with a flavored boson plus.
A flavored boson plus?
Yes, it's got that extra flavor to it.
Okay, and what does that flavored boson plus do?
Well, it does something similar to the top quark scenario. It actually converts that generic D into a generic U.
Through that electromagnetic interaction thingy.
Exactly. Yeah, but in this case, the total combinatorial value for the charm quark system, it just happens to equal 1.
So no extra mass factor.
Nope. So the charm quark ends up with a mass of just 2,000 electron units.
Okay, cool. And then we have the strange quark last one in this heavier group.
All right. The strange quark, it's a generic D, once again, at 200 electron units.
Okay.
And it's combined with a flavored boson 0.
Another flavored one.
Yeah. But here's the thing. The total combinatorial value for this whole strange quark system is exactly 1.
Exactly 1. So that means...
That means that boson 0, it doesn't introduce any mass factor.
Oh, interesting.
Yeah, so the strange quark just stays at its initial 200 electron units.
So if we look at this whole group, the top, bottom, charm, and strange, it seems like this model with those combinatorial values and mass factors, it does a pretty good job of like matching the order of masses that we see in the standard model, you know, with the top being the heaviest and the strange being the lightest in this group.
Right, and that's the really cool part about this model. It's like this really simple set of rules about how these combinatorial values work and how the bosons interact, and it seems to explain this huge range of masses.
Yeah, it's elegant.
It is. It's very elegant.
Okay, so let's shift gears now and talk about the lighter quarks.
Okay, to lightweights.
The lower generation quark, so the down quark and the up quark.
All right, so starting with the down quark.
Yeah, what's the down quark made of in this picture?
So it's got a generic U quark, which, as we know, has a mass of 2,000 electron units. And then it's got a boson minus.
A boson minus, okay.
And this boson minus has a combinatorial value of negative. So because we have that negative combinatorial value, the mass factor associated with this boson minus, it actually decreases the overall mass.
Okay, so instead of multiplying, we're dividing or something.
Yeah, you can think of it like that. So in this case, it decreases the mass by 200 electron units.
Wow, so we start with that 2,000 from the U subtract 200, and we end up with
10 electron units for the down quark.
10? That's a big drop.
It is, yeah. It goes from, thousands down to just 10.
Okay, so what about the up quark? That's the famously light one.
Yeah, so the up quark's a little bit more complicated. It actually has 2 different proposed configurations in this model.
Okay, 2 different recipes for an up quark.
Right, so the first one starts with a generic D, which is at 200 electron units.
Okay.
And then it's got a boson 0.
Right.
And that boson 0 divides the mass by a factor of 20.
So 200 divided by 20, that's 10?
Right, and then it also has a boson plus.
Okay, another one of those.
Yeah, and you guessed it, that boson plus converts the D into a U.
Through that electromagnetic interaction again.
Exactly. So what's the final mass in this scenario?
Well, it went from 200 down to 10 and then became a U.
It ends up at 5 electron units.
5? That's tiny.
It's one of the lightest particles out there.
Okay, so you said there's another way to make an up quark in this model.
There is, yeah. So in this other configuration, the flavored and generic parts, they essentially switch places.
Okay, so instead of a generic D, we have a flavored D or something.
You still have a generic D, but it interacts with the bosons in a different order.
Got it.
So you start with that generic D at 200 units, and you've got a boson plus that divides the mass by 2.
Okay, so down to 100.
Then there's a boson 0 that's made up of a flavored and a generic part, and that also divides the mass by 20.
So 100 divided by 20 is 5 again?
Exactly. So both of these configurations, even though they arrange the pieces differently, they still end up with a 5 electron unit mass for the up quark.
So 2 different paths, same destination.
Yeah. And they both result in what he calls a non-flavored system.
Okay, interesting. So again, this model seems to be doing a pretty good job of like matching up with the standard model.
Yeah, it's really remarkable.
Okay, so we've covered the quarks pretty thoroughly now.
I think so.
So let's move on to the leptons.
All right, the other half of the fundamental fermion family.
And we'll start with the heavier ones again.
Okay, so the heaviest lepton is the tau lepton.
The tau. Okay, what's it made of?
So it's a combination of a generic neutrino and a boson minus.
Okay.
Now, the initial mass of this generic neutrino is incredibly tiny. It's only 120/51,000 of an electron unit.
Wow, that's like barely anything. So how do we get from that tiny little neutrino to the big, heavy tau lepton?
For those combinatorial values, they come into play again.
Of course they do.
So in this case, the generic neutrino has a negative combinatorial value,
Okay.
and the boson minus also has a negative value.
So 2 negatives.
And remember what happens when you multiply two negatives together.
You get a positive.
Exactly.
Yeah.
So that means the mass factor from the boson minus is going to increase the mass.
By a lot, I'm guessing.
By a lot, yeah. So the boson minus, first, it converts the generic neutrino into a muon neutrino.
Okay, so it changes its flavor.
Right. And then that muon neutrino gets multiplied by the mass factor, and it ends up with a final mass of 4,000 lepton units.
Wow, that's a huge jump.
Yeah, quite a transformation.
Okay, what about the tau neutrino then, the tau's little neutral partner?
So the tau neutrino, it also comes from that generic muon neutrino.
With that same tiny starting mass.
Exactly. But in this case, it's paired with the boson 0.
Okay.
And again, we have that negative times negative situation with the combinatorial values.
So the mass goes up.
Yep. It ends up with a mass of 251,000 of an electron unit.
Still really tiny, but bigger than it started.
Right. And he also points out this interesting relationship between the tau and the tau neutrino.
Okay, what's that?
So the ratio of their masses, it's a factor of 160,000.
160,000, that's a big number.
It is. And what's really fascinating is that he suggests that this number might be connected to the mass of the W boson.
The W boson.
Yeah. The particle that carries the weak force.
Oh, right. Yeah.
So it's like there's this potential link between the masses of these leptons and one of the fundamental forces of nature.
That's really cool.
It is. It's very cool.
Okay, so let's move on to the muon then. What's going on with that one?
All right, the muon, so it also starts with that generic neutrino at 120,000 of an electron unit.
Hmm.
But this time it's paired with a boson minus that has a combinatorial value of 0.
Combinatorial value of 0.
Okay.
What does that even mean?
It means that this particular boson minus doesn't actually contribute to the mass.
Oh, interesting.
Yeah, so the only combinatorial value that matters is the one from the generic neutrino itself.
Okay.
And so the muon ends up with a mass of 200 electron units.
200. Okay, and what about the muon neutrino?
So just like with the tau generation, this model predicts that there's a mass factor of about 160,000 between the muon neutrino and the muon.
So that 160,000 keeps popping up.
It does, yeah. It seems to be a recurring theme in this model.
Okay, so now for the final two, the electron and the electron neutrino, and this is where the model seems to get a little bit different.
Yeah, it takes a bit of a different approach.
Okay.
So for this generation, it starts by talking about the muon again.
The muon, but we already talked about the muon.
We did. But in this context, it's considered to be equivalent to what he calls a generic electron.
A generic electron.
Right, because it has a mass of 200 electron units.
Okay, so the muon is like the starting point for the electron.
Yeah, you can think of it like that.
So then how do we get to the actual electron from this generic electron?
So it interacts with the scalar boson plus.
Okay.
But this time, this boson plus has a combinatorial value of 2.
Okay, so a positive value.
And since the generic electron has an implied negative combinatorial value,
we're going to get a mass decrease.
Exactly. And the mass factor in this case is a division by 200.
So 200 divided by 200 is 1.
Bingo. 1 electron unit for the electron.
Perfect. That's exactly what we want.
Yeah, it all works out beautifully.
Okay, and what about the electron neutrino, the littlest one of them all?
Yeah, so for this one, the model uses a slightly different starting point.
Okay, what's that?
It starts with the electron, but at an intermediate mass of 20 electron units.
20.
And then it interacts with the scalar boson plus.
Another one of those.
Yeah, which converts it into an electron neutrino and also divides its mass way down.
So how tiny are we talking?
Like 625 millionths of an electron volt.
Wow, that's ridiculously small.
It is. Yeah, almost 0.
And you mentioned earlier that 160,000 factor might be relevant here too.
It might be. So even though the starting mass is different, the model still suggests that the ratio between the electron and the electron neutrino masses
is in that same ballpark?
Yeah, it's roughly the reciprocal of that 160,000 number.
So even in this latest generation, that factor seems to be important.
It does. Yeah, it seems to be a fundamental constant in this model.
Now, we should probably point out that the standard model, it doesn't actually give us exact masses for neutrinos.
Right.
It just gives us like upper limit.
Upper bounds, yeah.
So these values that we're talking about from this model, they're kind of speculative, but they're interesting.
Yeah, it's a prediction of the model, and it's consistent with what we know.
So even though there are multiple ways to get to these final masses in this model, the underlying principles are still the same.
Exactly. It's all about these generic and flavored components and how they interact with the scalar bosons and those combinatorial values.
Okay, so to kind of sum all of this up, this model uses a pretty simple set of rules to explain this really complex pattern of masses that we see in the universe.
And it's not just about matching the numbers. It also makes this really interesting prediction about that 160,000 mass factor between the leptons and their neutrinos.
Which might be related to the W boson?
Exactly, and that could be a big clue about how these fundamental particles and forces are all interconnected.
It really makes you wonder about like what mass really is,
Yeah, what is mass at its core?
So our final thought for you, our listener, is this. How might a model like this, if it gets more support from the scientific community, how might it change how we think about the universe and the stuff that makes it up?
Yeah, it's definitely a thought-provoking model.
Yeah.
It is. It really is. So thanks for joining us on this deep dive. It's been a really fun one.
It has, yeah. It's been a good one.
Until next time.